Welcome, everybody. Tonight we're working on Unit 11. This is the first unit talking about deep learning. So we'll have Unit 12 will be Deep Learning 2, basically. And once we complete those two units, most of the content for the course will have been covered. I'm going to go ahead and proceed here. And we're going to talk about this. Is kind of weird. I think this slide is a little out of place. And I think there's a few flawed slides in here where basically this is the material we're covering here tonight. We're going to look at what deep learning is, a little bit of comparison with machine learning, or like really learning that deep learning is a subset of machine learning, a tad bit of the history, and then applications of how deep learning is used in a real world environment. As you see, it's a really important aspect of generative AI, and it's a very cool technology. Once again, that's a deeper level of machine learning. All right, let's kind of dig in here and figure out what this is. I am going to play this video. I did mention, by the way, and that this video repeats in this slideshow. And now I'm seeing the author's notes. Video to be played till 1:14, and then I guess we're going to resume it. What I'm going to do is I'm actually going to copy the video link from the notes in my slides, and I'm going to take us over to the Brave browser on purpose. And I don't know if you guys are familiar with this web browser or not. Some people do know about it. This is basically a variant of the Chrome browser. So it has the same code base as Google Chrome. However, it has built into it, out of the box, a really neat feature, which is it's an ad blocking, tracking blocking, etc. So it's stuff that you usually add plugins to your browser for to get rid of ads and stuff, are automatically built in and operate out of the box. It also has a way that if you opt to receive ads, that you can earn tokens for it and then use those tokens to buy other things from the people that support the browser. That's a whole separate field of study. I'm really a big fan of it, especially when watching YouTube videos that are riddled with ads, and that's been a problem during our PowerPoints, right? So I'll play one, and then an ad comes up and I have to apologize for it, and I'm kind of getting tired of it. So I'm just going to play the video from here. The author wants me to play it up to 1 minute and 14 seconds, and then we'll resume from there through the slideshow. All right, so here goes, folks. I'm going to bring it up. Let this load up here.
Ever wondered how Google translates an entire web page to a different language in a matter of seconds? Or your phone gallery groups images based on their location? All of this is a product of deep learning. But what exactly is deep learning? Deep learning is a subset of machine learning, which in turn is a subset of artificial intelligence. Artificial intelligence is a technique that enables a machine to mimic human behavior. Machine learning is a technique to achieve AI through algorithms trained with data. And finally, deep learning is a type of machine learning inspired by the structure of the human brain. In terms of deep learning, this structure is called an artificial neural network. Let's understand deep learning better and how it's different from machine learning. Say we create a machine that could differentiate between tomatoes and cherries. If done using machine learning, we'd have to tell the machine the features based on which the two can be differentiated. These features could be the size and the type of stem on them. With deep learning, on the other hand, the features are picked out by the neural network without human intervention. Of course, that kind of independence comes at the cost of having a much higher volume of data to train our machine. Now,
okay, so that's where the author wants me to stop. Now that I include into that, because I see it in the notes and I didn't see it before. Let's move on to the next slide. All right. So let's look at some of these definitions here. It says deep learning is a subset of machine learning. You just said that in the video, which is basically the neural networks that we've been looking at with 3 or more layers, right? Input layer, output layer, and then hidden layers in between, at least one hidden layer, sometimes more. It depends on the model that's being used. The neural networks try to simulate the behavior of the human brain, right? It's not really quite the same, but that's the model that we work from, and it's a good model, right? Obviously. Um, and basically it learns from large amounts of data. And this is one of the key aspects, right? Is the amount of data that deep learning works with. A neural network, it says, with a single layer can still make approximate predictions, but additional hidden layers can help to optimize and refine for accuracy. And that's why we have multiple hidden layers. We'll see like some different approaches tonight to doing this that makes it different from some of the previous neural network stuff that we looked at. It says it is a field that is biased on learning and improving on its own by examining the computer algorithm. So and I want you to think about this, it learns on its own and improves on its own based upon the algorithm that you build. So it's refining itself as it goes, right? Kind of like people do. And I think that's really cool. Machine learning uses, more primitive concepts than deep learning. And I think deep learning really is a better imitation of the human brain, as they're indicating here, than I think machine learning is. Neural networks are limited by computing power, and thus, as a result, are limited in their complexity, right? So, like, a simple neural network works on much simpler mathematical principles, and we're kind of harnessed a little bit by how much computing ability we can use on it, even with clever tricks like factorization and matrix multiplication and all that. The computing power has been a really big limiting factor in this area, right? We are now finally reaching the computer capabilities that are capable of really harnessing this stuff and working with it. And as we move forward, and if we hit the quantum computing era where that becomes like a practical technology, then you really have to watch out, right? Because then Skynet will rise and take over probably. It says advancements in big data analytics have permitted larger, sophisticated neural networks, allowing computers to observe, learn, react to complex situations faster than humans. And I think this is going to accelerate. The fact that we run a lot of these algorithms in the cloud, albeit expensive and power consuming, has really enabled a lot of the stuff that's going on right now in AI. Deep learning has been used in image classification, language translation, speech recognition. Those are big uses. And it can be used to solve any pattern recognition problem without human intervention. So I think that's really pretty intense to think about, right? If you compare it to some of the other stuff that we've learned about, like okay, if we're going to do machine learning, we can start with data that's already classified and say, well, this is a dog and that's a cat. Like you train a child, right? You give them a frame of reference. This is basically telling you that, well, we can do that without that intervention. That's kind of interesting. Now it says deep neural networks, the DNNs, right? So there is an acronym for it. Each layer can perform complex operations such as representation and abstraction that make sense of images, sound, and text. So each layer can be very complicated, much more complicated than in machine learning, right? One real big advantage of this, it works with unstructured data, right? Which is kind of implied in the definitions we were just looking at. It says machine learning only works with sets of structured and semi-structured data, while deep learning works with both structured and unstructured data. So it is more flexible. It can handle much more complex data and more efficiently. And machine learning algorithms typically cannot. So it is much more powerful. And you can see the graphic on the right there where they're showing you kind of like how the inputs, and then you got like the humans in the middle, right? Us messing up the whole process. And the networks are typically pretty simplistic to get the output. Deep learning typically will have many layers. Some of those kind of like recirculate on themselves, and then they look at their own output within the network and then revise the previous inputs to make it even better every iteration. So it definitely makes it more powerful. Um, with feature extraction, machine learning algorithms use label sample data, right? Like dog, cat, like we talked about. Deep learning will take large volumes of data as input and analyzes that data to extract the features rather than the other way around. You see the difference there. So it like can look at huge volumes of data and pull the features out. You know, like what am I noticing? Why is this animal different than that animal? You know, why is it a dog or a cat or a, I don't know, a mouse, whatever. The best performance, right? The performance of machine learning algorithms decreases the more data we feed to it. So to maintain performance of the model, we need deep learning. So this is why it was basically developed, is because machine learning has some limitations because of the mathematical algorithms that we're using. This attempts to overcome that. Well, not attempts, it overcomes that aspect of it. Okay, we're going to go back to the video here. And I'm looking at the instructor's notes here in the slides. So I'm going to go back to the video and we're going to resume.
Now, let's dive into the working of neural networks. Here, we have 3 students. Each of them write down the digit 9 on a piece of paper. Notably, they don't all write it identically. The human brain can easily recognize the digits. But what if a computer had to recognize them? That's where deep learning comes in. Here's a neural network trained to identify handwritten digits. Each number is present as an image of 28 times 28 pixels. Now, that amounts to a total of 784 pixels. Neurons, the core entity of a neural network, is where the information processing takes place. Each of the 784 pixels is fed to a neuron in the first layer of our neural network. This forms the input layer. On the other end, we have the output layer, with each neuron representing a digit with the hidden layers existing between them. The information is transferred from one layer to another over connecting channels. Each of these has a value attached to it, and hence is called a weighted channel. All neurons have a unique number associated with it called bias. This bias is added to the weighted sum of inputs reaching the neuron, which is then applied to a function known as the activation function. The result of the activation function determines if the neuron gets activated. Every activated neuron passes on information to the following layers. This continues up till the second last layer. The one neuron activated in the output layer corresponds to the input digit. The weights and bias are continuously adjusted to produce a well-trained network. So, where is deep learning applied? In customer support. When most people converse with customer support agents, the conversation seems so real, they don't even realize that it's actually a bot on the other side. In medical care, neural networks detect cancer cells and analyze MRI images to give detailed results. Self-driving cars. What seemed like science fiction is now a reality. Apple, Tesla, and Nissan are only a few of the companies working on self-driving cars. So,
all right. So they, as part of the slide that we were looking at, they talk about some other, and if you look at the notes section of the slide, talk about self-driving cars, news aggregation and fraud news detection, natural language processing, virtual assistants, entertainment, visual recognition, fraud detection, healthcare, personalizations, detecting developmental delay in children, colorization of black and white images, adding sounds to silent movies, ATM, automatic machine translation, automatic handwrite generation, automatic game playing, language translations, pixel restorations, photo descriptions, demographic and election predictions, and deep learning, or deep dreaming, excuse me. Those are some other possible applications here. Now I'm going to jump back to the PowerPoint again, and let's take a look at the history timeline on this a little bit, and notice that it says, in the 19th century, people started to ideate this stuff, right? That, okay, well, we're making machines that are self-powered, either by steam or fossil fuels or electricity, and the machines perform actions. And they had this conception that maybe machines one day could be as intelligent as humans. In the 50s, they started working on this issue. They started conceptualizing the neural networks and how we might actuate that, either in machine form or electronic form or whatever. By 1990, we're actually using machine learning models. So there were models that were deployed that were helping with, most notably, optical character recognition. And actually, even in the 80s, it was pretty effective. So like the thing they were showing, like where a person like writes a character, and a really great example is like how we write the number one. Some people just make a slash. Some people put the flag at the top. Some people put the flag at the top and a foot at the bottom. That type of thing. And then there's all the different font faces of printed materials. They all look different. And to develop software that long ago that could look at characters on a page and go, oh, that's the letter M, and then convert it into the electronic format. That's pretty amazing considering the primitive computing technology, but people have been working on these problems for a while. By the time we got past the early 2000s, we finally started getting the computing power that we need to really utilize all of these technologies, including all three levels of AI that they're showing here. The general AI, machine learning, and then deep learning. Deep learning, though, you'll notice really, people were tinkering with it in the 90s and early 2000s, but the computing power was really pretty limited. We didn't do a lot of cloud computing back then, and the technology, if you wanted to utilize it, was super expensive. Now we're reaching the point where, heck, any of us can go onto Azure or AWS, Amazon Web Services, and spin up virtual machines and run machine learning environments if we have deep enough pockets and do crazy stuff. It's just a matter of the ideation and the money to do it. Heck, even the machines that we have now at home, in some cases, are possible of doing this stuff. And I'm going to, I think I was grading a couple things earlier, and I'm sorry I didn't get everything graded, but I got a lot of stuff graded. Where people were running some of the algorithms and they were like, it was taking a really long time. Or some people were like, oh, I ran it and it just didn't finish, that kind of thing. And, and this reminds me of kind of like the old days when we would render video or something. And that process was so time consuming. We'd basically start the process, go to bed, and then hopefully next morning it would be done, that kind of thing. And people want everything to happen immediately now. But if you're processing a really large amount of data, sometimes it takes a really large amount of time, right? Especially with the primitive technology that we have at home. When you use cloud computing, you're clustering computing environments together and you're using, a ton of power, a ton of computing resources, and thus the cost being really high. But it is possible now. And now companies like NVIDIA are starting to build GPU-based computers that are designed to do all this stuff, right? And GPUs work a lot differently than CPUs. Let's watch the rest of this.
Deep learning has a vast scope, but it too faces some limitations. The first, as we discussed earlier, is data. While deep learning is the most efficient way to deal with unstructured data, a neural network requires a massive volume of data to train. Let's assume we always have access to the necessary amount of data. Processing this is not within the capability of every machine. And that brings us to our second limitation: computational power. Training a neural network requires graphical processing units, which have thousands of cores as compared to CPUs. And GPUs are, of course, more expensive. And finally, we come down to training time. Deep neural networks take hours or even months to train. The time increases with the amount of data and number of layers in the network. So, here's a short quiz for you. Arrange the following statements in order to describe the working of a neural network. A. The bias is added. B. The weighted sum of the inputs is calculated. C. Specific neuron is activated. D. The result is fed to an activation function. Leave your answers in the comment section below. 3 of you stand a chance to win Amazon voucher.
Okay. Well, obviously, we're not going to do that, but I think it's kind of interesting. We will look at the answer in a little bit. All right. So moving on from here.
Ever wondered how Google translates an entire web page to a different language in a matter of seconds? Or your phone?
Okay, there we go. Sorry about that. All right. So let's take a look at the comparison of the two. So deep learning basically separates itself from machine learning by the type of data that it works with and the methods that it uses. So machine learning algorithms are generally leverage structured, labeled data to make predictions, right? We've talked about this. It goes through some pre-processing to organize unstructured data into a structured format. Sometimes it's a manual process, right? And I don't know if you guys remember like what we did in the AI class where like we were like using that one online tool where I was like holding up different objects and training it, like this is masking tape and this is an orange, or I forget what objects I use, but you know, something weird like that. But there's a pre-processing that goes through it. Deep learning eliminates some of that pre-processing, and it can on its own ingest and process unstructured data like text and images, feature extraction, and then basically removing us from the equation and having us being needed to do it. And I think this is fascinating to think about. So like some of this magic Gen AI stuff that we're dealing with is based upon this. I mean, obviously at some point we're starting with information in a knowledge base, but at some point it crosses this threshold where we're kind of removed from the equation. It's like, yeah, Mom, Dad, I don't need you to tell me what that is. I can figure it out on my own, right? Right, because maybe you don't even know, but your child eventually figures out how to teach itself. So they have this comparison here, right, where they're comparing machine learning and deep learning, and the feature extraction originally in machine learning will happen from us, right? And they're saying dog, cat, hamster, whatever. And the deep learning algorithms figure it out on their own. So they'll look at it on their own and go, okay, well, what makes these things different? You know, and machine learning once again requires that human piece, right? Like let's watch this video. This is a different video. I'm going to try to, I'm still kind of hesitant to do it here. I'm gonna, you know what? I'm going to play it here because it starts midstream. It doesn't start at the beginning. So let's just flow from here. And I think actually they want us to start about here.
Examine how the term deep learning
They have like a timestamp on here.
Relates to all of this. What is deep learning? Deep learning algorithms can be regarded both as a sophisticated and mathematically complex evolution of machine learning algorithms. This field has been getting lots of attention lately in the mainstream because there's been an explosion in deep learning technology. Deep learning describes algorithms that analyze data with a logic structure similar to how a human would draw conclusions. This can happen both through supervised and unsupervised learning. To achieve this, deep learning applications use a layered structure of algorithms called an artificial neural network, ANN. The design of such an ANN is inspired by the biological neural network of the human brain, leading to a process of learning that's far more capable than that of standard machine learning models. This is what a simple artificial neural network looks like. The leftmost layer is called the input layer, the rightmost layer is the output layer. The middle layers are called hidden layers because their values aren't observable in the training set. In simple terms, hidden layers are the calculated values used by the network to do its magic. The more hidden layers a network has between the input and output layers, the deeper it is. In general, any ANN with 2 or more hidden layers is referred to as a deep neural network.
Okay, so that's really the piece we're trying to extract here. 2 or more layers that are hidden, turn it from machine learning into deep learning, right? And if you add like a third layer, and it just causes basically more and
Applications
more
of deep learning.
iterations. And I apologize once again. All right. Um, Here we have, these are just general questions for discussion. And, there's a bunch of different ways that this is happening. And I'm not really here to necessarily answer those questions, but you could research this. A lot of businesses are using this technology now to improve their metrics and things that they were doing in so many different ways, right? The fact that it's getting into the range of affordability is changing the fact that people who are reluctant to use it because of cost or lack of knowledge are now delving into it because it has the prices come down significantly, right? And the fact that we have all this Gen AI that we can use for free as well, right? That helps, right? Including really cool machine learning and deep learning models online that you can just play with and see what happens, So I think that's pretty fascinating in and of itself. All right, so we're going to go into this concept now of multilayer perceptrons, and they have an acronym for that too. And we're going to hit all these bullets here. All right, so some of this stuff is very much a repeat of content we were looking at last week. And so here's my commentary on the slideshow. Clearly, whoever did last week's is not the author of this week's. That's what I'm seeing in it. So some of the information is somewhat redundant because we've already looked at networks. We already understand the basic principles of them, but reinforcement doesn't hurt, right? Perceptrons are the smallest unit of the network. And they do certain computations, right? So we take the input data, we hit, the perceptron, they travel over different pathways, all the next layers all connected up, and then we end up with output. The pathways are weighted, right? So there's like values to them, and that helps to make the determination of what output that we get. And there's often, what they call the threshold logic unit. And we usually have a separate function. If you guys remember the sigmoid function, where there's like a threshold that we trip to make it true or false, on whatever scale we're using, to follow that pathway. Otherwise, we don't, right? This is a supervised learning algorithm, and it classifies data into two categories. So it's a binary classifier. Once again, the true false aspect of it, right? It separates the input space into two categories by a hyperplane. You guys remember that's like a weird plane that we can't envision in regular two-dimensional space, represented by the equation. There's also bias involved too, and we'll look at that as well. Okay, so because it's a binary classifier, it separates the input space into two categories, right? Because of the fact that it's binary, we can also apply what we call logic gates. So this is like computer science weird stuff, right? So gates in computer science, where you're doing like circuit level design, is basically like which pathway you're following. And there's different kinds of gates, like ones where you can follow both pathways, or ones where you one pathway or the other, or variants called an and. And I'm not here to teach you those specifics right now, but if you ever formally studied computer science where you do like circuit level design, they get into this stuff. This is like the realm of electronics. And this is why like electrical engineers often have to do programming, and why computer scientists often have to learn electronic circuits, the same reason. But it's fascinating because there's a kind of like this interrelationship between like CPU design and the concepts that we're using here. It's all interrelated, right? It's not accidental. It's based on math, electronics, and logic, right? But the binary classifier, the true false, is often very common in electronics. So we talked about these feed forward neural networks when we talked about machine learning, and that's where your input comes in and the data travels in one direction. It only goes forward through the network, right? It can't backtrack, right? We may have hidden layers, we may not. We don't really know. but the data is still moving forward. When we are using hidden layers, we can have single hidden layers or multiple ones. We've been kind of talking about that, but the data flow is still forward. It never goes back. So in other words, when I get past the first layer, whatever it hidden or not, when I'm on the next layer, what happened on the previous one is irrelevant. It's only what's happening now that's relevant. Okay. And that you'll see with deep learning that will change. All right. So they have these goofy little graphics in here, but they show you like you know, how it basically works, right? They're summarizing data, they create a bias, it trips the threshold function, it's either true or false, and then we have an output, right? But notice like the one perceptron might have multiple data paths coming in. Each one of the data paths coming in has a value on it, right? We summarize those, whatever mathematical formula, maybe we're adding them together, maybe we're looking for the largest, maybe we're looking for the average, it really depends. Then there's a bias value, usually related to the perceptron itself. And then if it triggers our threshold in the sigmoid function, then we have the output. But ultimately, we're looking for a true false response here. Right. The weights of the data coming in are static. That means they cannot be changed. This is part of the feed forward thing, right? Where you're going to see in deep learning that they can be adjusted, and it's self-adjusting actually. So the function basically operates like that graphic, and I think that's a really cool little graphic. We also have multi-layer perceptron networks, right? So we have a bunch of inputs, and then we have a couple hidden layers or more, and then we basically funnel down to one output. It'll go through the network, as discussed, depending on how complicated those hidden layers are. Every node is connected to all the other nodes on the next layer, right? We did all this stuff. We talked about all this already. Input and output layers are present having multiple hidden layers, at least 3 or more layers in total. Input, output, and at least 1 hidden, maybe 2 hidden or more, right? But remember, when we get past 2 hidden, then we're talking about deep learning. All right. Here's kind of the interesting thing about this one. All right. So multi-layer perceptron networks have bidirectional propagation, forwards and backwards. Now that's a little bit weird. So like what they're trying to say here is once I come past the inputs and hit that first layer, this layer has the capability the next time it runs to alter the values of these pathways and basically adjust the network the next time around. And it'll keep adjusting it and adjusting it and adjusting it until it figures out. So it's kind of like, like how we learn as humans. Like, how do you learn how to ride a bike? I get up, I fall over. I get up, I fall over. I tried this, I fell over. And eventually you figure it out and you're upright, right? But how'd you figure it out? By readjusting how you're doing it, right? How do you get up on 2 wheels? Well, you got to stay in motion is one thing. And the other trick is don't look down. look to where you're going. This is like the trick of being on a motorcycle too, right? You look to where you're going, not to where, you don't look to the ground because then you end up on the ground, right? Notice that the activation functions, the ones that move you on to, basically follow nonlinear formulas, which is kind of interesting. All right, I think we're at a good stopping point here. So we're going to go into this next. So we're going to go into convolution neural networks, but we are going to take a 5-minute break first. So I'm going to pause the recording, and I will see you guys in 5 minutes. Please take a break and step away from the machine. All right, let's continue on. Back from break. All right, so we're going to review this topic. And if you guys remember, we talked about this pretty early on in the Intro to AI course, very, very briefly. And we're going to hit all these bullets here. But convolution neural networks, all right, so we call these CNNs, and no, it's not the news service, right? Also known as convnets, and I'm not sure how to say that, so I'll just stick with the CNN, right? and it shows here multiple layers and are mainly used for image processing. And you'll notice as it kind of filters through these matrices here that they get a little smaller and tighter, right? This was first developed in 1988, and it was used for optical character recognition and basically for reading things like zip codes. And if you guys know any history, thank you, right? So I'm not sharing my screen. So no, I hate that because what happens is my face is full screen. So uh, I'm going to actually backtrack a little bit if you guys don't mind, because I can fix this in post, as they say. Right. So we're basically going to hit these bullets here. And I think YouTube allows me to take a little section and cut it out and remove it. So that's what I'm going to do, by the way. And, so here's the multiple layers, the graphic I was starting to talk about. And when they first developed this, basically for doing OCR work, and at the time, back in the 80s, it was a thing at the post office, right? Before they would put these little like weird barcodes on the bottom where the letters were pre-encoded, they would actually have human beings look at every piece of mail for the zip code, and then they'd type it into a machine and then forward it to the right destination. And I think this is really fascinating because I have a friend that was a very good friend of mine that actually did that job, exactly that job at the post office. Eventually, people started printing these things on the envelopes that kind of did it automatically, and they had like readers, so the zip code was converted into this kind of like barcode looking kind of thing. And if you look at your letters now, it's still there. And when it goes through the system, it like automatically sorts. But every once in a while, there's like, the card from grandma where she still writes it out by hand, and he still processes those. So he's still got a job. He's about to retire, I'm sure, by now. But, but they also had developed a machine before those codes were there to kind of do that reading. So I think that's kind of interesting. We use convolution neural networks to look at satellite images, process medical images, forecast time series, and detect anomalies. And I think that's pretty interesting because I did have some procedures or tests done on my heart earlier this year. And they had a tech who was operating the machine. And I was watching the screen she was using, and the thing was like pointing out stuff that she should highlight. She wasn't making a decision. The machine was telling her what to highlight, like what might be something to look at, which I thought was fascinating. So apparently there's some of that technology embedded into that machine or the software that runs it. CNNs provide, it says, a more scalable approach to image classification and object recognition tasks. And they use linear algebra, basically matrix multiplication, to find patterns within an image, right? And we've talked about this a little bit already. They're distinguished from other neural networks by their superior performance with image, speech, and audio signals inputs, right? So these do really well with that type of thing. And, it says here it requires GPUs to train the models ideally, right? And it's not that you couldn't do it with CPUs, but GPUs, as we saw in that video, tend to have more processing cores, right, than a standard CPU. And a lot of our consumer machines, like we're only like spending $1,000 on a laptop or a desktop, it's not going to have that kind of power. And those of us that are gamers, like you buy a system that has a great CPU and RAM and a hard drive and all that, but then you get this killer graphics card so you can play games really well, right? And that's like a whole thing. But GPUs are in high demand. They're used a lot for doing a lot of artificial intelligence work. So they build machines with a bunch of GPUs just to process AI stuff. It's also used for like, Bitcoin mining and things like that. Once again, because there's more processing capability. They are a lot more expensive than regular CPUs. But if you have a computer that, that's a good computer, but doesn't have a good graphics card, you're kind of like not really have a good computer, basically. But now they're starting to use those GPUs, and I mentioned this before, like NVIDIA is starting, I think they may have already released them, starting to release machines that are built around GPUs entirely for the purpose of doing exactly these types of tasks. And therefore, instead of people having to farm this out to the cloud, might be able to buy the machines to do it locally. And I think that's really kind of a fascinating thought, kind of exciting, actually. All right. So it says, the architecture of a traditional CNN, right? Basically have the following layers, and they show first the convolution layer, then the pooling layer, and the fully connected layer. And you'll see how that kind of like breaks down from one to the other, in stages, right? So the convolution layer, that's the core building block, and that's where most of the math happens, basically. We have a few components in that aspect, which are the data that's coming in. There's a filter and a feature map, and we kind of basically use the filter over the feature map, and we kind of like do these computations by shifting the filter around the feature map and basically perform math and adjust its position as we go. And you'll see some graphics coming up here. And then it gives us a resulting matrix. So we're doing mathematical matrix operations again. And I think the graphics really kind of show it pretty well. But when we do this, we kind of look at things like dimensionality. And so we have, usually a rectangular square matrix of some sort, and it may have multiple dimensions, or it may just have a singular dimension. I think all the examples are singular dimensions. And those are then adjusted by a certain amount each time. They call that the stride. So like, are you shifting it by 1? Are you shifting it by 10? What, how are you shifting it? And they use the example of pixels, because it works well with the matrix, right? And I think that's one of the reasons why we have that. So if you watch like the graphic here, as the filter is the yellow part, right? And it's taking the input data, which in this case is an image, and as it moves 1 pixel at a time, right? Then it goes down a row 1 pixel at a time. It takes the values inside the matrix and it seemingly is adding them, right? And then we get a smaller matrix with combined values, right? And so this is kind of what's happening. And so the matrix on the right is kind of the byproduct of the filter operating over the input data. And you notice that, the names that they're using for this stuff. And it says the element involved in carrying out the convolutional operation in the first part is called the kernel or the filter, right? So interchangeable names, or K, represented in the yellow color. So there's multiplication and addition happening here in this matrix, right? And so what they're trying to show us now is that when we're working with a matrix, and we want to cover a certain amount of depth on it, it will move a certain number of times. And typically when we're doing a stride, it's going to be set to 1. We want to shift 1 at a time, because that way it becomes really methodical and follows a pattern that makes sense. So it says every time performing the matrix multiplication between K and a portion of P of the image, the kernel is hovering. And I think the next one has an animation here too, right? And so here we have, and this is really kind of interesting because this is representing how pixels work on a screen. So like, this is really kind of weird. The computer screens that we're all looking at right now are made up of tiny little squares. Each square can be one of 3 different colors, right? And in reality, that pixel on the screen has 3 different light emitting components to it that are all present in a layer, right? So they could be red, they could be green, and they could be blue. And then depending on how strong they are, they compose our screen. So if like if you have a HD screen like I do, Mine is 1920 pixels across, 1080 pixels tall. And like this math that you see happening here is taking, that filter, running it over the pixels, right? And then coming out with these different outputs. And what happens is we look at the values for red, the values for green, and the value for blue. And some of them are additive, some of them are subtractive, but we end up with a net amount, which gives us the output that we see on the screen. This is really kind of what they're trying to demonstrate here. I want you to kind of conceptualize that this kind of math is happening on our screen a minimum of 60 times a second per pixel, right? So why do we need really powerful graphics cards? Because man, look at all the stuff it has to do, right? And and we talked about this last week too. I think like if you have a higher refresh rate, like 144 or something like that, it's happening that many times a second. I mean, it's just mind-boggling, when you think about it, and that humans are smart enough to even create this stuff, right? But these filters are operating over 3 dimensions of the matrix, combining the math and then still outputting it to a simpler matrix. And so this is kind of like giving us what the output of the combined 3 are. This is really fascinating stuff. So this is one aspect of how convolution networks work. All right. There's also what we call hyperparameters, right? And it says that affect the volume size of the output, before the training begins, right? So that includes the number of filters, right, that we're going to use. And it says, for example, 3 distinct filters reveal 3 different feature maps, creating a depth of 3. And the stride is the number of pixels the kernel moves over the input matrix. And it says, while a stride of 2 or greater is rare, a larger stride yields a smaller output. It makes sense because you're skipping, right? Whereas if I'm going 1 pixel at a time, then your output is going to be larger, right? And so it depends on what your goal is ultimately. There's also what we call the zero padding thing, which we use that when filters don't fit the input image, right? And it puts all the elements in the matrix to 0, producing a larger or equally sized output. That's kind of weird. There's 3 types of padding, right? There's valid padding, same padding, and full padding. The valid padding is also no padding. So we aren't really using it. It's the last convolution is dropped if dimensions do not align. And it says the same padding ensures that the output layer has the same size as the input. And full padding increases the size of the output by adding zeros to the border. Okay, so all different techniques used for different reasons. We also do pooling of layers. They call this downsampling, dimensionality reduction, basically reducing the number of parameters in the input. The pooling operation sweeps across just like the regular filter operation does. This filter has no weights. No, really all it's doing is it's aggregating values. And, if you take a look at what the filter is doing and then, what the output is, so 3x3 pooling over a 5x5 convolved feature, right? So what is the result? It reduces complexity, more efficient, and limits the risk of overfitting. 2 approaches, basically. And there's not only 2, but these are the main 2 that people use. They either look at each one of the boxes here and look for the max value, right? So we're looking, so for example, if I take this first collection of 4, what am I finding for max? 20. So that's the output. What am I finding for max? 30. What am I finding for max? 112, right? Or I can average the results. I can take all of these and average them and come up with a result, but there's a pooling of the values. So it's kind of truncated or, summarized in a sense. Different outputs, if you look at the relative values, are these relative values similar? No, not really, right? Once again, it depends on what your goal is here. And just and it says, as an aside, this approach tends to be used more often compared to average. So people tend to use the max pooling approach more than they use the average pooling approach. All right, we'll talk about fully connected layers. And basically, this is where we take maybe a matrix like this and flatten it out. And then each, basically part of that matrix becomes the inputs that then feed the network. So if you take those 9 squares that are in the square and just flatten them out and then feed them into the perceptrons and the layers of the neural network. And it says, fully connected layers are found towards the end of CNN architectures. And, it says you can optimize it to optimize objectives such as class scores, right? So we're looking, once again, that there's that keyword optimization, right? Like we're looking to optimize values as a result of this. So in this approach, each node connects directly to the node in the previous layer, like in all neural networks. It does the classification based upon the features it extracted through the previous layers and their different filters. And so, the filters from the previous layer have a byproduct effect on what's coming up. So that's different now than the ones that are the feed forward that don't look backwards. This one is affected by what happened before. And it says it usually leverages a softmax activation function, but it still works on this probability of 0 to 1. And there is some threshold that you would set to trigger it. Usually it's halfway, right? 0.5 might trigger it. So if it's past 0.5, horseshoes and hand grenades, basically. Sometimes that can be adjusted too, though. There's different types of CNNs. And if, by the way, if you look in the notes for this particular slide, there are links to some of the sources for this material. And okay, so it says a large number of these variants have emerged with the introduction of new data sets such as MNSIT, the CFAR10, and then ImageNet, and a couple of these others. Some of these others include the ones that you see here. You'll notice like Google has one, and there's a lot of big companies that have their own on these that have engineered them. And then we're going to move into recurrent neural networks, what they are and the different types. Now, this is where this gets interesting. In this graphic, basically, the animation's a little obnoxious, frankly, but the hidden layers here are basically condensed down to one little thing in that, animation. Basically, that there's a loop back within the hidden layers. So stuff is being processed on those layers and the information is moved back and used. And notice how the recurrent neural network is useful. It uses sequential data, right? So data that is in a sequence or a time series. So things that are like timestamped or things that happen in a specific order, right? And it says that they're commonly used for ordinal or temporal problems such as language translation, natural language processing, speech recognition, and image captioning. So in other words, ordinal means it's basically not like a typical numeric type of thing, right? We're looking at qualities as opposed to precise values. And things that happen over time, right? So for example, the words I'm speaking to you now are spoken in a specific order. So when I say, when comes first, I comes next, say comes after, and each one of those is broken down into pieces too, right? So they're looked at in that sequence. It says it works on the principle of saving the output of a particular layer and feeding it back to the input in order to predict the output of the layer. So for example, if I use Siri, right, to ask a question, and Siri gets to learn how I ask my questions, it can kind of become a little bit predictive as to how I speak and react to me relative to me as an individual, right? Because I have certain patterns that I speak in. Also, the way that we speak a language is different depending on your language, right? So if any of you, who know how to speak English and also know a different language like Spanish or whatever, right? You know that sometimes it's like, well, we ask or say a sentence in a certain order, and then you say it in that language, and the words are in different orders, but you're saying the same thing, right? And Greek is very much the same way as that. Like it's not always in the same order, and so it adjusts to that. All right, it says the different nodes of the neural network are compressed to form a single layer of recurrent neural networks. It says A, B, and C, and those are these little lines here, right? So the input, the output, and the loop back are all there. And the ABC, the input, the loop back, and the output are things that are tweaked in this model to improve the output of the model. It's like, well, this is what happened this time. Let's adjust, see what happens this time. And it will, because they're parameters, they can be adjusted. And I'm getting a little tired of that animation, frankly. I wonder if I can stop it. I guess I cannot. Like the feed-forward networks, the recurrent neural networks utilize training data to learn. So we have to seed it, basically. So like in other words, like if I'm teaching it language, I have to give it a language reference to start with. Like, hey, here's English, this is how we do English. Or here's Spanish, here's how we do Spanish, right? And they use that information from prior inputs to influence the current input and output. Right? And it says traditional deep neural networks assume the inputs and outputs are independent of each other. Output of the recurrent neural networks depend on the prior elements within the sequence, like the order of the words I'm speaking, right? They have more meaning relative to the other words that came before and the words that follow. So they have context. And this is really kind of what this recurrent neural network brings to the table. Right. So it says, consider the scenario of reading a book, right? With every page you move forward into, you need the understanding of the previous pages to make complete sense of the information ahead in most of the cases, right? So, you're not one of those people that goes to the last page of a mystery novel and reads like who did it, right? Because it might make no sense, right? It would make more sense in context. In a feed-forward network, the output of what happened on the previous page has no impact on what's happening on the current page or the current sentence. That's kind of the difference. So feed-forward networks cannot be used when predicting a word in a sentence, as it will have no relation with the previous set of words. It has no context. Recurrent neural networks, this challenge can be overcome because it is looking at what just came before, and it's recognizing its place in that stream or that sequence of information. Right. All right. So why were these created? They were created to handle some problems, basically. Neural networks, especially the feed-forward ones, could not handle sequential data like what we're talking about. It only looks at what is current. It doesn't memorize what came before. So that's why this was developed. And I think the key aspect of it is that it memorizes what came before so that it can process things going forward and make sense of them. And so what they're showing you in this graphic here, and this one takes a little while to propagate, is we have that thing with the hidden networks, the A, B, and the C. The B, the C loops back, and then the A becomes the output. And then we move on to the next piece of information, but it doesn't forget what came before. It doesn't ignore it, right? Both within the model of one iteration and as it moves forward through the sequence. So this has memory, right? Like a human being does. Like I heard what you said. I heard when you said it. I remember what you said before. That process is iterative. If you look at the notes section on this one, that has a lot of information on it, but I think we've already talked about it all, so I'm moving on. So some places where we use this stuff, and this is kind of interesting for sure. It says recurrent neural networks are used in image captioning, and they have an example of that coming up, I think. So in other words, you look at like a website or like some sort of a news feed, and they have a photograph of, I don't know, the floods in Texas, let's just say. And underneath the image, right, and this is kind of required by a lot of screen readers and stuff, they have to have a caption describing the image, right? And a lot of times those are not written by human beings. It takes time. So you have a piece of software, you feed in the image, it goes, oh, look, there's a man saving a person from a flood, that kind of thing. It looks at the image and makes that analysis and then gives an output. Also, it's used in time series prediction, and it says here like predicting the prices of stocks or Bitcoin or something like that. Very heavily used in natural language processing. Text mining and sentiment analysis is often based upon recurrent neural networks. Also, machine translation. So in other words, given an input in one language, these networks can be used to translate into different languages as output, right? So, and I'll use that example again, like in one language, you order the words one way, and in a different language, you order them a different way, right? So converting the words, and you're also converting the order. And I think that's pretty fascinating. A bunch of different types of these, right? And this, in database people, you guys will recognize this terminology when it comes to forming like table relationships, where recurrent neural networks kind of have the same features. And we have this one-to-one, one-to-many, many-to-one, and many-to-many types of connections here. The one-to-one recurrent neural networks have a pretty simplistic model. They call this the vanilla neural network for whatever reason, probably because it's so plain. It's used for general machine learning, and it says a single input and a single output. Right. One piece of information going in, one piece of information going out. The one-to-many is starting with a single input, and then it has, notice the different sequences here, right? It might iterate a few times, and then we have different outputs, right? Well, that's a picture of a man saving somebody from floodwaters, but it's also a picture of a tree inundated with floodwaters, and it's all, whatever, it has many aspects to it. And this is the image caption tool, right? Because it's trying to recognize all the stuff that's going on. You gave me one picture, and I'm telling you all the stuff that's happening in the picture. We have the many-to-one, so we might have a whole bunch of inputs, and we're only really looking for one output, right? So the movie was exciting. The movie had great dialogue, and it had a great director. Did you like it? Yes or no? Yeah, yes. That type of thing. Lots of inputs, but you're only really looking. Should I go see the movie? Yes or no? One singular output. So sentiment analysis is a good example. But you can also have the situation where you have a bunch of inputs and a bunch of outputs, and machine translation is one of those, right? Because I could input an English sentence and get Spanish, or I could input a Spanish sentence and get Greek, whatever, right? So it could have a lot of different inputs and a lot of different outputs as a result. All right. So here is an interesting little question that they're putting in here, and they're not providing a slide on it, which I thought was a little bit weird, real frankly. So earlier today, I did a prompt on this first question: what is a vanishing gradient and an exploding gradient problem in RNN, and what's the best way to deal with it, right? So what I did, and this is kind of a goofy way to do it, because where I captured it it wasn't probably the best place because I just dropped it into my Notepad++, and this is kind of an ugly looking program, but it's a basic text editor. And I'm going to zoom in on it a little bit, and we'll just kind of look at it in a basic sense. So there's the thing called a vanishing gradient and an exploding gradient problem. It says here, two significant challenges encountered during the training of recurrent neural networks, especially when dealing with long sequences of data, and they both relate to the behavior of gradients during back propagation, right? So when it's looping back, and how they adjust their weights based on the error. So when they loop back and they run, those hidden layers again, they're adjusting their values, right? Like you getting on the bike and trying to ride it and go, well, the first time I leaned this way, and the next time I leaned that way, and then you adjust. So the vanishing gradient problem occurs when the gradients, the values that indicate how much to change in network weights, become extremely small as they're back propagated through many layers or time steps. This happens due to the repeated multiplication of small numbers, often derivatives of activation functions like sigmoid or whatever, and then which have a maximum derivative of certain values, right? How it affects RNN training, difficulty learning long-term dependencies, slow convergence or coming to an answer basically, and limited learning capacity. The exploding gradient problem is the opposite of the vanishing gradient problem. It occurs when gradients become extremely large during back propagation. And that happens if the weights in the network are large or poorly initialized. So the values that went in originally weren't very good. And their repeated multiplication causes the gradients to grow exponentially, which we don't want. So this causes training instability, divergence, not an answer, basically. We're moving away from an answer, not towards one. And poor performance, right? And why they're susceptible, because they iterate, basically. And if we're always applying the same set of weights, the problem can compound, basically. Common solutions, gated recurring units and long short-term memory, right? So we use different architecture, basically with gates, to control the flow of information. So in other words, if we learn, hey, I'm getting up on the bike and I'm falling over, let's just not do that one. That's what they're talking about. They're flipping a switch and they're saying we're not going to follow that pathway. Do we also figure out where the threshold in the activation function resides, and we adjust it so that it doesn't trip unnecessarily one way or the other. And then we try to set better values going in, and there's techniques for doing it. All right, so what's the best way to deal with the gradient problems? If you look at the slide notes, it says use the long short-term memory network is basically the answer. Does this come up with the same answer? This is from Gemini, by the way. All right, so it says dealing with vanishing and exploding gradient problems is crucial for effectively training, especially here are the popular efficient ways to tackle these issues, right? For vanishing gradients, I think was the question, right? Gated recurrent units, right? That's the one solution. The ReLU approach, batch normalization, proper weight initialization, and then, they kind of go on and on. In practice, a combination of these techniques are often used. For RNN specifically, that's the one that they're referring to in the slide notes. So long short-term memory network, GRUs, along with gradient clipping, are the most popular and efficient ways to handle gradient problems. Right now, whether or not we understand what that means is a matter of practice, right? So these are, getting into mathematical formulas here, folks, and those formulas do get deep. But we're introducing ourselves, right? This is introduction to machine learning, not master's level machine learning, right? So it's a process of learning that we're going through. All right. So we learned about the different algorithms. Now we're going to learn some of the potential of this technology with generative AI. Now, if you guys recall, from the first course. We talked about GANs, right? Where we had the generative adversarial networks, where we have them create content, right, from nothing, basically, from a prompt. And then they also have a discriminator built within them that takes that and analyzes it to see if it's fake, right? With its objective being to generate content that isn't easily detected as being fake. That's what this graphic shows. So we start with data and we build upon it and we generate out to whatever. And then we backfeed that information and deconstruct it to see if we can figure out if it's good or not. Is it phony or is it real? And with the goal of it, of course, being to like kind of minimize the fact that it recognizes that what it created was false, right? Kind of an interesting concept for sure. All right. So the generator network takes random noise as input and generates images that are progressively refined through the layers. The discriminator network tries to classify the generated images as real or fake, right? Remember talking about that a little bit in the other course? Yeah, we did. That attempts to show some of the layers there. Another application is text generation. So RNNs are used a lot for sequential data generation. Language fits into that, right? Both the letters of a word and the words of a sentence and the sentences of a paragraph, etc. Because they have a memory that enables them to capture and generate text based on the context of the previous words. So for example, like Gateway gave me access to Grammarly. And one thing that Grammarly does is I can come up with an idea, a topic for a paragraph, like, pick something, right? Homer eats a donut. And what might the next sentence be, right? And based upon what I already did, it looks at it and can kind of confabulate something, right? Why? Because it remembers what came before, right? The process, basically, it takes the sequence of an input, the words or characters, and generates the next word or next sentence in the sequence. The output of it is fed back along the model to generate a coherent sequence of text, right? In this case, they're using an input image, right? And this is an attempt to do the captioning tool. They use the convolution network. They have a feature vector. They use some linear equations. They use the long short-term memory thing to minimize the gradient issue. And then what they're noticing is that there's giraffes, that they're standing, and whatever, there's trees and grass and, whatever it is, right? And then you come up with an output, right? So this is not taking words as an input. It's taking an image as an input and turning it into words. This is kind of a fascinating thought, right? So there's this tool out there, by the way, called Simplified. You can Google it. You can try it online for free. It's just out there. There are paid versions of this, and big publishers use these types of tools to caption their images automatically. And for example, if you feed an image in, like you just drop it into a box, and it asks here, what's your photo about? And then it generates a caption, like you tell it, okay, it's an image of a sunrise. All right. And then it looks at that image and says, witness a breathtaking sunrise where the world seems to come alive, and, like it's a lot more flourishy and whatever. I don't know how many of you have maybe even watched videos online. And I've noticed my wife watching a few, and they'll show some stuff on the screen, and clearly somebody in a foreign country generated it, and they didn't want to translate it, and it's an AI that's kind of reading the content to you. And really what that AI is doing is it's looking at the images and doing generating captions on the fly on a video, which is a sequential thing. So it's a sequence of images being converted into a sequence of captions. I think it's fascinating, right? And there's a lot of stuff, a lot of tools out there like that now, and I think it's really bizarre. We use this for speech synthesis as well. So for example, let's say I had a video and I didn't know English. I just knew Greek, right? And I typed up all my words in Greek for the video, captioning the video. And then I could run a tool that would turn it into English and match up with the captions I already created. These models are trained, and they're pretty crazy powerful. Like one tool that was talked about a lot at the Summerfest Tech Conference, in a couple of the things that I went to, people were talking about Google Notebook LM, which has a feature where you can take text like a paper that you typed up for a class and turns it into a podcast so you can hear what it sounds like. And not only does it turn it into like speech, but it also like puts inflection in it, you know, like if you're writing a character story and then John said, "Look out," it sounds emphatic, you know. John said, "Look out," it's not like that. John said, "Look out," those tools are out there for free. That's a product you guys can try without paying any money either. So the speech recognition process also works in reverse, right? Like where if I'm like talking to a voice assistants, at least in the past, we used to have to train them. Or if I used drag and dictate in the old days, like back in the 90s, I had drag and dictate. And I had to spend a couple hours like reading words to it and saying sentences to it before it figured out how I spoke and it would convert stuff. Now, oh my God, like, Siri doesn't need training. If I go to Google and do a search, it doesn't need training. It just understands me. Right. And I won't do the thing where I say, "Okay, Google," and then my phone says, and it's doing it already. All right. And now it's going to.
What is your phone doing already? Can you describe the issue?
Yeah. Sorry, Gemini, be quiet. Right. Yeah. So we played with those things, right? So voice assistance is one thing. So like really on my phone, I'm triggering Gemini and it's kind of my voice assistant because I don't use the one that comes with my phone. But really I'm triggering an AI and I'll ask it like search questions and stuff. And I do use that quite a bit. Another thing that it's used for a lot is audiobook narration. Or how about like when you guys are inside of Brightspace or a bunch of different, like websites now, like I think even the Gateway website has this, where you can have the website read the text to you, like if you're hard of seeing, right? It can read it to you. Or maybe you understand it better if you hear it rather than read it. There are people that have that issue. And once again, the fact that we're getting this narration now and it actually has inflection in it, I think that's pretty wild. Some of it sounds really, really convincing. Here's another tool that they're recommending called Speechify. If you guys want to go try this, and with this, you can just drop your text in. So this is kind of like this is like the Google Notebook LM thing that I'm talking about, but you can take words and just drop them in and just have it listen to you, I think that's pretty fascinating. And I'm trying to see how many slides I have left. Maybe I actually try this one. But fun tool to try for sure. It's not the only one out there that does this. And a lot of our Gen AI engines are capable of doing this stuff now just by asking them, by the way.
Deep.
We're just about at the end here. We are at the end. So actually, let's go back and try that too. I'm just going to grab the URL out of the notes section here. I've never tried this particular tool, so I'm doing it kind of on the fly. And let's see how it goes. See how easy it is to get in there and try it, right? Let's try it for free. And now I'm going to need some text, right? To drop in there. Okay, now it's going to make me. Is this one okay? So now I'm thinking, did we try this in the first class? This is seeming a little familiar to me. No, you guys are all shaking your heads. I'm just thinking, can I find some content here easily? All right, how about we do this? I'll just take these words here to try it. A lot of steps. All right, I got to go with Snoop.
What up, though? It's Big Snoop D-O-double.
That's just killing me.
What up, though? It's Big Snoop D-O-double G, and I'm an English voice from the United States.
All right, I guess I have to create an account. I'll just sign in with my Google account. Steps, the steps you have to take, right?
It's a pretty cool app. You can also like take pictures of text and it will read it to you. I used it a lot when I had to read a whole bunch of articles for class, and it was
Oh,
easier to just listen to them instead of just reading them.
but now they're asking for money. Yeah.
Yeah, it's
You
expensive.
got it, Laura. I'm not going to pay. All right. But I was so looking forward to Snoop Dogg reading my notes from class, you know. But you guys, you know, if you want to try it, you're willing to put your credit card in there. And Susan, I assume you went ahead and paid for it. Is that a fair assumption?
It was like 70% off if I it was a free trial, and then I canceled and they did the whole try it for 70% off, and then I did it and then I canceled it again.
Gotcha. All right. Well, folks, that's gonna do a wrap here for tonight. Go ahead and play with those tools. I know that if you use the Google Notebook LM, you can do some of that stuff for free, and there are other ones. I just don't have handy links. So please don't hesitate to try tools like that. Just really quickly to look at the content in the core shell in terms of assignment. We do have some dependency files here. I don't think this one is particularly difficult because they're starter code files and you're just basically changing values and then running these. So there's two tasks. One is to adjust the initial bias to these various levels and then compare the results, right? Tell me what you see. And then also to adjust the learning rates to these various values and tell me what you see. It should be pretty easy tweaks. You can feel free to go ahead and use Gen AI if you wish. I don't know if it'll be necessary here, but I think this is a pretty straightforward assignment. Unit 12 hopefully will be released maybe as soon as Thursday or Friday, and then I'll get the remainder of the content. But that's a wrap for Unit 11, and we are done for the night. We have a few minutes to spare, which is pretty rare. All right, so this video ends here.